Hi, welcome to Signal Path. In this episode, I have another repair for you guys. This is an Agilent 33250A, which is an 80 megahertz arbitrary waveform generator function generator, and it's actually a pretty good unit. And Agilent or Keysight still sells these, and they're not that cheap. This one doesn't turn on, doesn't work. And a friend of mine gave this to me as a broken unit, and I promised him to make a video of it, of the repair of it. So let's go ahead and take a look at it and see what happens. As I said, the symptom is that you plug it in, you push the power button, nothing happens. This guy has a soft power button, so it doesn't have a one that disconnects the line from the unit itself, which means that there is some circuitry in there which takes care of the soft power on and all that. So that, for example, that could be one of the causes of failure. We'll take a look at it. One nice thing is that the schematic, the full schematic of this unit, is actually available on Keysight's website for free for the 33250A unit. So we can actually have a complete schematic of it. What we don't have is the schematic of the power supply. So unfortunately, that's a third party vendor that they've bought the power supply from. I assume. I haven't seen what's inside it. So anyhow, let's go ahead and open it up and see what's going on. So taking this apart was really straightforward, because all these units that have this particular shape from Agilent or Keysight, they always operate the same way. You can see I've opened it a little bit before I fully take it apart. They have these back units which have two screws which hold it in place, and there's another screw at the bottom. So like this, you should be able to slide this off. So I'm gonna go, there we go, I'm gonna try that. One thing I noticed that this is actually a really heavy unit. At first you don't think it would have so much mass, but it's actually quite heavy. So there it is. You can see some nice copper tape here, which really isolates and connects, grounds really well the chassis to the case on the outside, which is fairly common. We've seen this in multiple different things that I've opened in the past. So go ahead and let's take a look at this. The top of it is fully covered, and you can see that there is a warning symbol here, so most likely the power supply, something is underneath there. These are ground connections to the ground of the chassis, so these are actually safe. You can touch these, it shouldn't be an issue. I'll show you more in detail. Let's see what's underneath it. Oh my goodness. Wait a second, let me get this handle out of the way. Wow, very interesting. At the back there is a lot of passives back here. There is resistors and capacitors everywhere. There's almost not that many ICs back here except for the passive, so everything must be on the other side. There's a couple of Samsung memories here. You can see two footprints that haven't been occupied. I wonder if there is an option that you can add more memory to this. I'm not sure, I haven't checked. Whole bunch of tandem capacitors around. It looks like this is mostly passives, but clearly double-sided. I don't see many through holes on this, but it should be interesting to see what's on the other side of it. At the back of the unit, if I can get a good view of this, there we go. You can see that this unit actually was manufactured at a time where the USB wasn't part of the series. So this actually doesn't have a USB port. It has an RS-232 GPIB, which you can use with some wave builder software from Keysight to download your own arbitrary waveform directly into the unit itself. There's of course 10 megahertz in and out, modulation input, and external trigger, FSK burst, and so on, interfaces to the back of the unit. And this is a 100 to 240 volt. It would work basically anywhere in the world. So pretty nice and standard. The fan at the back. You can see if I hold it at this angle, you can see some plastic. This is plastic, this is not metal, so this is not a heatsink. Some plastic cover, so I can see from this angle that the power supply is actually mounted on this piece of metal. So when you remove that, you'd remove the power supply with it, and I can see some ribbon cable, which most likely runs down to the unit itself. So should be pretty easy to further disassemble this. It looks like there's only one screw, which is the same screw that was at the back of the unit, actually same torque screw. So let's go ahead and remove that. So we should be able to slide this off. Wow, this is really stuck in there. Oh well, that hurt quite a bit. Here we go. Let's see. Aha, see, just like I thought, you can see the power supply fully contained there at the back. And I'll give you a close look at everything in just a second. So let me go ahead and place this down, and we'll take a look and see plenty of various ICs on the top of that PCB. So here's everything. I just placed this on top of the base to hold it up so that I don't strain the ribbon cable that comes from the main motherboard. And you can see that the only connection from the external, from the line AC to the unit is through the power supply itself. There is no other interaction to the main PCB. And you can see the two line and the earth ground coming onto this power supply. And then the power supply has a ribbon going back. So this power supply is one of those units that produces a whole different range of voltages, all the voltages that essentially you would need on the main motherboard. You can see that if you look here at a quick scan, there's only very little circuitry that would be a DC-DC converter of some kind. Everything else is internally generated from this board itself. And it's interesting to take a look at the power supply also, because the power supply has clearly a section that's blocked off by this plastic piece, and again there is another warning symbol on top of it. So whatever is underneath this portion is sitting at a high voltage, whereas these heat sinks probably do not. And it's not plugged in, by the way, right now. So, you know, probably touching these wouldn't matter. But before we get further, I have to warn you, you have to be extremely careful playing with these power supplies. As you know, there are lethal voltages present, and even though I'm in North America and 120 volts, it would be even more dangerous in some other parts of the world. Please be very careful, and then I'll give you some other hints along the way of how I plan to probe this if I need to. And so I guess my strategy would be to let's just plug it in and try it again, and let's see what happens. And then we can go ahead and look at the schematic of the main board and see what the circuitry is that's responsible for turning the unit on and off. And then that's probably a good place to start. Okay, I've gone and plugged it in, and you know, I pressed the power button, and of course nothing is happening, just like before. But something interesting I noticed when I plugged it in initially, you know, sometimes when you plug in a supply you hear the tiny spark at the point where there's a rush of current inside the unit. I heard that, so which means there is some rush of current inside it at some point. And no, it was a very small sound, so it's normal. You hear it all the time with this type of you know, switching power supplies. It's normal to hear that. So yeah, obviously some signal, at least some voltage, is getting into the power supply itself. So we can go ahead and probe that later. But before I do that, let me just quickly show you the schematic portion of where the switch is responsible for turning on the unit. That would be a good place to start, and we can also investigate some other features. And then don't worry, I'll give you a quick look at the motherboard afterwards with all the different ICs on it. But let's focus on fixing it first. So the schematic of this unit is organized into based on functions, and subsystems of different functions are in different pages, which is very useful when you want to look for something specific for a particular component. Let's say, you know, if I'm looking for a fault in the crystal oscillator for a time base, I will go to the time base schematic, for example. So I'm not going to go through every single thing, but we can see the different subsystems that they have broken the schematic into. So this is the first page of the schematic, is the earth referenced communication portion. So that's not the part we need, so we can keep going forward. This is the main processor schematic. Still not what we're looking for, but this is the portion where the main microcontroller essentially has an overall view of everything that's on the main motherboard, communicating with everything, setting up different links between different components. So that's still not what we want. Then there is the main gate array schematic. Still not it. Display controller. Well, I don't know if the display has worked because it doesn't turn on. Still not what we're looking for. The DSP. No. The modulation schematic. Nope. System DAC, no, that would be the DAC that of course generates the output. Still not, we're looking for the time-based schematic. Still not it. The phase lock loop, no. The trigger, nope. Clock divider and control, still not it. Synthesis IC, no. Waveform memory, synchronous multiplexer, no. Digital waveform, sync, variable edge trigger, blah blah blah. Waveform DAC, multiplier, multiplier schematic, no. Main output circuitry. Still not it. This will be interesting to take a look at some point to see how the main output is connected to the main motherboard, see what the final stages are, which of course require tight requirements on linearity and so on. Power supply. There we go. There's one more. This keyboard. And the display, still not it, and the component placement. One thing I noticed about the PCB is that it doesn't actually have a silk screen on it, which is really a bit annoying. So to find all these components, you have to go back and forth to this page, and you can see the front and the back. So let's go back to, there you go, power supply. So we can take a closer look at this. So if you look at this page, I hope you can see it, but I'll focus on the part that's important. I'm looking around in here, and I can see that there's a main connector. So there's a power cable. This is our ribbon cable. So that's very useful because now we know the interface between the power supply and the main motherboard, so we know what to focus on. And obviously, the portion of the the circuit here that shows the soft power switch would be of most interest to us. So let's go ahead and focus a little bit on that. See what we got. So let's take a look at this guy first. There it is. So here's our connector. This is a 45 or 49, 50, I'm sorry, it's a 50 pin connector, ribbon cable, so there's 50 different wires in it, and you can see that most of those wires are actually connected to each other because there are the digital common grounds and analog common grounds and various things, so most of them are in parallel, of course for current handling capability and so on. So what usually happens in soft switches is that a portion of the power supply obviously needs to be on, because there's a portion of it that needs to provide some level of power back onto the main motherboard in order for that switch to be active and so that there'll be a way for them to actually detect a soft button press. Now that's not always the most power efficient way, because it means that when you plug in the instrument, that is always going to be part of it is always going to be on and burning electricity, and you want to minimize that as much as possible. That's why I usually like when instruments have a hard switch, or at least have the option of having a hard switch, so you can permanently turn it off if you're not, constantly turning it back on and off. So, but sometimes it's also, they do this for other reasons. For example, in cases of a frequency counter, what they do is that they have a part of the power supply always on, and they run the oven controlled crystal oscillator always at temperature. This has two benefits. The first benefit is that when you turn the unit on, the crystal is already warm and ready to go, so you're at your nominal calibrated temperature, so you get the most accurate frequency reading. Also, the temperature cycles, thermal cycles of crystal oscillators is actually quite bad for them, and they age that way, and they drift apart and they drift away from the frequency that you want. So that's another reason why they do that. But this doesn't seem to have that, although it does have an oven-controlled crystal oscillator in it, which I will show you. So if I were to follow this, I can see a couple of important things. For example, I can see that the power on switch is right here. And this means that we should be able to take a look and see if this button actually is working. I don't think that that's a problem, because there's really not that many reasons for these things to fail. It's not like the button is being used all the time anyway. But you can see that it comes into this as an NPN transistor, where you can pull this node down to ground and then turn the NPN transistor on or off or so on, and then that goes on to a relay in here, and that relay essentially locks once you press the button once, and that keeps the unit on, and then you press it again, it turns it off again, because it's all the coil is controlled by two things at the same time, and that way you can turn it on and off. It's a very, very common soft switch power on circuitry. Now, what is useful for us is that we have two things to test now. Because we know where the switch is, we actually can go ahead and see if you're getting any electricity into the unit at all. Because if there is no electricity coming in here, there's no way to turn the relay on and off. There has to be some standby voltage coming into the main motherboard in order to operate this whole circuitry. So we can look for that and see if that's coming into the unit at all. If it's not, then we can eliminate the main motherboard and all of these things altogether, because that's most likely not the problem. And I actually just saw that. If you look here, oh, sorry about that. There we go. I don't know if you can read it, but here, let me actually zoom in here, might even be better. There we go. Look at that. There is a power on line, and there is a 12 volt SBY, which is standby. So if this 12 volt standby is not there, then forget it. Then the motherboard is not the issue. You have to start looking at the power supplies. That's a very good place for us to start. So let's go ahead, and I can follow this 12 volt standby. If I go ahead and follow that, you can see that it comes all the way up to here, and then it goes here. Look, it's pin number 13. So if I go ahead and look for pin number 13, I should be able to easily see if the main power supply is working at all. And there's another thing that I can look at, and there is also the power on. Here we go, this power on. This power on is the node, is essentially a signal coming back into the power supply, telling the power supply, okay, now you can fully power on with everything on there. So even if we do see that the 12 volt is there, we can take the power on signal and ground it, or connect it to 12 volt, I have to double check, and that way we can actually force the power supply to turn on ourselves without the motherboard, and then we can find out exactly where the problem is. So there's a couple of neat things for us to try. So these power on and standby signals come from two pins, and they are pin number 11 and 13 next to each other. there you go. That's pretty good. That's a good place to start. So let's go ahead and see what we can get. All right, everything is plugged in, ready to go. So I can, of course, it still doesn't turn on, so I can go ahead and again be careful. This is actually live. Well, I'm telling you to be careful. I should be careful. This is live, but it should be. I'm going to be fairly cautious here and disconnect this ribbon cable from the unit, like so. There we go. So now we don't need this anymore. So now by doing that, there's basically nothing connected to the main motherboard to the power supply anymore. It's fully independent. The only reason we even have to have this close by is because of the convenience of having this cable. So I can see from the side here that there's a little label on this power supply. Again, I don't have the schematic, but I can see that pin number 1 starts on that corner. So I can go ahead and plug the ground into one of the ground pins, like ground. This is pin number 25. I can go ahead and plug that in there. So there's our ground. You can leave that hanging out. And then I can count from pin number 1 and go ahead and I think it was pin number 13, if I remember correctly. And we can go ahead and see if there is any voltage at all on that pin. So we have pin 1. Make sure I'm holding this in my hand. Pin 1, 3, 5, 7, 9, 11, and pin number 13, like so. There we go. Now, although it doesn't look like it, but my fluke meter is actually connected to these two. The cable is running right underneath this. You can't see it because of the lack of space here. So there we go. Connect our ground to that, and connect our VDD to that. And well, nothing. Hello? No, nothing. I don't get anything. So that's actually good, because this means that we can pretty much isolate our entire debugging of this from this unit itself, because I'm not getting the 12 volt standby that I should be getting from this unit, meaning that this is not powered on in some way or it's faulty in some way. And of course, if there is no 12 volt going into the motherboard, how can this guy ever turn the power supply on? That's impossible. So that's a good step forward. So let me go ahead and disconnect that from here. Get the camera in the way, it's a little bit difficult. Anyhow, there we go. You get rid of these cables. So next step is to take this power supply completely out of this case and put it on the side and just take a look at it by itself and see how it's constructed. So here's the supply by itself, and there's a different angle of it. So let's go ahead and take it apart. I can see that there's a label on this main cap here that has some information on it, probably from the manufacturer. It's a little bit hard to read as it is, but I'm going to take it apart and separate it. Now, one thing is that again, even though this is not plugged in, you have to be careful when you disconnect it, because this will hold charge for some time. Now, here's a really subtle point that people may not pay attention all the time. Normally, these capacitors, main capacitor that's on here in a soft power supply like this one, will be charged up to to something almost 200 volts or so, depending on where you are. Then it will automatically discharge, because there's always some power consumption in the unit because of the soft power on option. So there's always a little bit of leakage current turning on, for example, that 12 volt power supply, which will then discharge this capacitor quickly. But if that part of the circuit isn't working, there's nothing to drain this capacitor unless they have purposely placed a resistor, a leakage resistor across the capacitor to discharge it, which means that this can actually hold charge for a very long time because it is faulty. So you have to be very, very careful. It's a little subtle point that doesn't always come up, but you have to be careful. So let's go ahead and disconnect this, and I can already see a fuse in there, but I don't think that fuse is blown. Like I said, when I plugged it in, I heard the little tiny spark sound that these power supplies make when you plug them in. So at least the signal is getting to the power supply based on that little observation that I made. So we can find out if that's the case or not. And you can see it's reasonably nicely manufactured, but you can see the style of this power supply, the style of the layout and the style of the manufacturing is quite different from the rest of the board, because it's not made by Agilent and Keysight. It's all outsourced away. So let's see. There we go. Disconnect all of that. So this guy should come out in some way. Still seems to be held in some way. Oh, I see. There's a center pin. You have to slide it. There we go. If I can get this guy out. There it is. There we go. Oh, look at that. So you can see at the bottom They have an insulating layer. Even though there is standoffs, they do this just in case so that they don't short at the back of the supply to this. So that's good practice as always. There we go. Now we have this guy. Now we should be able to get this plastic piece off as well. Aha, there it is. There is our power supply. There you go. Let's take a quick look at that. Nothing fancy. The PCB slides in these corners so that this thing stays in place. There is no pressure on this from the screws. They go through the holes, but it stays on there to protect you. I'm assuming that this part of the circuit is live and quite at a high voltage. We'll measure it, and we'll find out. So here we go. Nice. There's a little power supply. It looks rather complicated because it produces so many different voltages. So it's made by Power One power supplies. Let me see if I can get you little specification of it. There it is. You can see that it can 50-60 hertz, 100 to 240 volts, and it gives you 5 volts up to 7 amps, 16, minus 16, minus 5.2, plus 12, so on and on and on. And I'm assuming that you see that last plus 12 at 0.1 amp, that's probably the standby. I could be wrong, but I think that might be it. And there it is. It's quite nice. Everything looks good, and that's our main capacitor, of course. And let's see, you can see right down there, it's a 105 degrees Celsius rated, and its capacity is 470 microfarad at 400 volts. So nice and good. And of course this is at 400 volts, even though I, being in North America, would never charge it to even close to that. But of course if you're running this from 240 volts, then you're expecting something along the line of 240 times the square root of 2 voltage roughly sitting there. So that can be quite dangerous. So here we go. You can follow the signal path, no pun intended. Right there you can see there's a line input, some protection MOSFET circuits. Here's our main AC capacitor from there, and there's some inductors, and there's some more protection circuitry. Here's a bridge. Here's a bridge rectifier right there. You can see classic 4 there we go. Classic 4 outputs. There's the symbol for the rectifiers on the other side, so you cannot see it, but I'm fairly sure that's what that is. You can see from here that all the thick traces, these are the traces which carry the AC, and then right when you're here after the rectifier you're in DC, and this big thick traces is what the total amount of current for the entire supply has to flow through these two. And then it gets to there, and then the rest is switching. So we can go ahead and follow that pretty easily. And here's our fuse. There we go. Like a little fuse. Looks like a 5 amp fuse. Here it is. 5 amp, 250 volts. Nicely there. There you go. Nothing, not a big deal. Doesn't look like it's blown. So all nice and everything. So here's the main inductor for the switching power supply. Here's some board that's sitting at the back right there. It's actually kind of weird when you look at it, because there's a gap in here, and I would imagine that this should be connected, but of course I had never taken this apart, so I don't know what's going on over there. But anyhow, shouldn't be a big deal. A bunch of other stuff. There's a couple of potentiometers around, and here's the main circuitry that controls the main DC-DC converter right here. So this UC, let me see what the part number for that is. Let me see if I recognize that. What are we looking at here? This is a UC3845N. I think that is I think that's a DC-DC power supply control IC, which controls the switching of the main MOS transistor, which I believe is this one. This main MOS transistor is what is connected to this main transformer here, which then does the switching power supply action by doing the PWM and all the necessary stuff. And I believe that's what that IC is. But what I think is that this part of the circuit, in my opinion, should not be active, because this part of the supply with this main large MOSFET and the heatsink and everything is the main supply. So this will only turn on when you enable the whole unit. So this shouldn't be on at the beginning. Something else is generating the 12 volts that is responsible for turning on the power supply, the standby 12 volts. So we have to find out where that is. And we should be able to perhaps even trace it very quickly from here. But you know what, before I do that, let's just do a couple of measurements on here. Let's see if we get any voltages at all, and then we'll try and trace the 12 volt supply. Here we go. I've plugged it in, and it's upside down so that I can easily access it. And of course this table is isolated, so you can see the lines coming in, and I have set my my Fluke 289, whose battery I just needed to change. to AC voltage. So we can now go ahead and trace and see if I see any voltages. It's going to be a little bit difficult with the camera in the view, so I'm going to try my best to not kill myself. So here it is. So this is the AC input. Obviously we expect to see, there we go, no problem. 126, perfect. We can go ahead and follow that trace, and this is our fuse right here, this gap, and oh, my hand is in the way, here we go, this is our fuse gap right here, so it should, the fuse is okay, so we should be able to see the same voltage on the other side. Here we go, look at that, there is a 123, no problem. Here's the inductor on the other side, we should be able to see the same voltage again, because it's just passing right through it. There we go, 125, still good. So now it jumps over, and we can continue that, and this is at the input of our bridge rectifier, the 4 inputs that I showed you. So if I measure here, I should still see the voltage. There you go. So this is where the AC voltage will end. I expect to see if the bridge rectifier is working, which could be one of the things that's failed, for example, that I shouldn't be able to see any voltage after that. So let's go ahead and switch to DC voltage, and these 2 pins that you see right here are the 2 pins of the capacitor. You can see there's a hole in the middle between them. So there is where I have the 400 volt capacitor there. So I expect the square root 2 of 125 or so to appear on this side, which is I guess maybe around 160, 170. So here we go, I can go ahead and measure that. There it is, look at that, 168.5 volts. So everything up to this portion of the circuit is working, meaning that our bridge rectifier is working, our capacitor is good. If this capacitor, for example, was bad and it was a short, then it would have blown the fuse by now. So that's most likely not the issue. And since I see a nice steady voltage there, I'm not worried. So then now we can just go ahead and follow this and see where it goes on the other side. I can see, it reaches all the way up to here. And oh, here's another thing. This big blow-up solder that you see, and you can see there's 3 of them, that's the heatsink. So you can see this heatsink is actually sitting on the voltage of the capacitor, and that's why that cover was there, because that heatsink is sitting, is live, and it's extremely dangerous. And please be very, very careful. And if I go ahead and measure this heatsink from here to the ground chassis of the whole thing, you can see that to earth I see 82 volts on it right off the bat. So it can be quite dangerous, and of course between the chassis and the other input of the capacitor you're going to see 168 volts. So be cautious. So it looks good, so I'm going to go ahead and turn it off, and let's see, let me show you this capacitor issue that I was talking about. So here's the capacitor. You can see that it's sitting at 168 volts. So I'm going to go ahead and turn off the power, and I have actually a switch on my foot because it's connected to an extension cord, and if I turn this, I'm also going to lose some of the light, so it's going to get a bit darker, so that's why. So here we go, there you go, I just turned it off. Look, you can see that it's fairly discharging fairly quickly, I guess. That's okay. And you can see it's still sitting at 45 volts and it's slowly going to go down, so you have to be careful. I turn the light back on, what we're going to get is going to jump back to 170. There it is. So it's, it's all good. So just be careful. So now the next thing to do is to go ahead and follow the 12 volt trace that is supposed to be the standby voltage, and see where it is on this actually connected, so we have a new place to probe. So let's go ahead and trace the 12 volt standby supply. So this is pin number 1. If I flip this over on this side, you can see that here 1 is labeled. That's how I know this is pin number 1, and you can also see it by the ribbon, the red line on the ribbon cable. So there it goes. So we can go ahead from here and count our way and see where it is. So let's see, it's a 1, 3, 5, 9, 11. So I lost count. 1, 3, 5, 7, 9, 11, 13. Here we go. So this is it. This pin right here is the one. It's actually, I'm lucky because the trace that's connected to that pin is on the bottom layer. There's a few traces on this side too. There's a double layer board, so it makes it a little bit more annoying. So it could have been one of the other traces, but it's not. So we can go ahead and follow that. So if I go ahead and follow, this is the outer trace. And the outer trace, if I follow, go ahead and can go and see it's always on the outside. And it comes right here. And what is that on the other side? That's a capacitor. And there is two different capacitors. There's an electrolytic capacitor. It looks good. It doesn't look like it's blown. It looks it's intact. So we can measure that afterwards. But I can see that it connects to this trace. And this trace connects to only two things. One thing is on the other side, it goes to a point in here. And on the other side, on the same place, I have a diode right there, down in there. But more interestingly is this component. This component, this component right here is actually a resistor. If I flip it over, it's that resistor right there. And if you look at the colors on that resistor, it's a red, if I can see it, it's red, brown, black, which is 200 ohms, I believe. So that's a 200 ohm resistor, which means that's just maybe a protection of some kind, just to make sure that the current draws not too much. And then it connects to these. And so this pin right here is the pin that I'm interested in. And look at that. And what is that? That is this board. Aha. This board right here. This seems to be the board that is generating our standby voltage. So now we have a definitive place to investigate, and you can see it has its own coil, its own transformer for its own DC-DC converter, it has its own MOSFET, it's entirely fully self-contained, and it only connects to the main board via very, very few points. It doesn't actually have that many interface points. So let's go ahead and measure at the output of there and see what we're looking at. Because I have a feeling that if this is the board responsible for the standby, that is where our problem is, and we should be able to find it. And you can see it's kind of loose, but anyhow, let's see. If I'm looking at this here, you can see the joint, the solder joint that it connects. I mean, it looks okay. Doesn't seem to have any problems. There's several of them here, and they all look reasonably okay. So let's go ahead and power this back on and see what we get. There we go. I've gone ahead and plugged it back in again, just like before. So here's our meter. There we go. Sorry about that. There it is. So we can go ahead and measure. So again, as just to show you that it is on, there it is. You can see 168 volts again. So let's go ahead and probe at this point right here, which is supposed to be the 12 volt output, and which goes to this capacitor, and then I followed that trace. So if I go ahead and pick a ground node in here, these are all ground, as I showed you from the schematic, they're all connected together. You can see that there's a copper flood covering everything, so this heatsink is ground. So I can go ahead and measure that, and where was it? Here we go, right there. 12 volts. Wait a second. It's there. I don't understand. The 12 volt is back there. Well, let's follow it up here. Still 12 volts. So actually, across this capacitor, we do have 12 volts. So the capacitor is okay. So what is going on here? Why wasn't it working before? Let me see. Let's take a look at, maybe the trace is broken. Let's look at the actual here, the voltage here. Pin 1, this one. Look at that. It's actually there. The 12 volts is back. I fixed it. I don't know what I did, but it's back to life. I don't understand what's going on. So look at that. It's working out of nowhere. That's frustrating. So I did exactly the same test I did before. I connected it to the ribbon cable, and you can see that VC 12 volt. This is the same test I did at the beginning when it was still connected to the main motherboard. So it still works, and so the only thing I'm left to judge is that something I did mechanically fixed it. Maybe because this board was loose. So I'm going to go ahead and pick something like something that's plasticky, and then I'm going to kind of shift this around and see if this voltage actually ever disappears. So what I have here is this actually wooden. So I'm going to hold the corner of the board here. I'm going to try and press this, see if we can make it fail. Well, it doesn't seem like it wants to fail, but I can't push it very well from this angle that I am. Let's see. Look at that! Look at that! I just pushed it forward. It just came back. Look, I just pushed it forward. Now I can't do that again. I just did it 2 seconds ago. No. Oh, there you go. Look, I can make it fail. Look, it's just dead. I just exactly like it. It's still connected. Everything turned on, and you can see it doesn't come back on anymore. So if I fiddle with it, I'm sure I can make it come back. Come on, you can come back. Anyhow, well, there you go. That's it. That's what is causing it. This board is either not making good contact with the main motherboard, or something on the board itself is bad. So I can go ahead and remove it and resolder it back in and clean it and make sure it works. But anyhow, I'm sorry about that. I was hoping for a more exciting problem. This is a really boring problem. But anyhow, nonetheless, let's go ahead and remove it and clean it and put it back in. We can still take a look at the motherboard and do some other experiments. So let me show you something to drive home the point that I was saying before. So right now it's actually still not working because I guess I didn't push it hard enough for it to come back to life. So you can see that the 12 volt is not there. It's sitting at 0.17 volts. And if I look at the voltage across the capacitor, that voltage is still sitting at 170. Now remember I said that you could have a problem if this is actually faulty, it can be more dangerous. Before, I guess the first time when I turned it off and I measured the voltage, it must have been on and it must have been working. So let's go ahead and try again. You can see it's 170. I'm going to do the same thing. I'm going to turn off the light with my foot and you can see the discharge. Look, it doesn't discharge. It stays there and drains very, very, very slowly because its only discharge path used to be the standby DC-DC power supply, which is right now disconnected and not working because of the mechanical fault that it has, or the cold solder joint or whatever. So you can see how dangerous this is. This is all turned off. So right now if I were to touch it and do something with it or accidentally short something, I'd have to discharge that entire capacitor. So be very careful. A faulty power supply like this one is still sitting at 157 volts, how slowly it's discharging. Be very careful. This is the point I was trying to tell you before. I'm glad that we caught the issue so I can show it to you. Alright, here we go. We're at the soldering station. I'm going to use the ACO 407B for this job. And while this thing warms up a little bit, I'm going to go ahead and apply a little bit of flux to these points. So the only points I need to desolder are these couple here. So, and just go ahead and give this guy a little bit of flux, making it easier to remove it from the board, and then we'll clean it up afterwards thoroughly. And it's important that whenever you do something like this, of course, that I use the right tools for the job. Of course, I have a few different diameters for this desoldering station, 0.8 millimeter, 1 millimeter, 1.3 and 1.6, which helps you get the closest, tightest grip around the pin that you're trying to unsolder, so that you can get the maximum of the amount of airflow, the suction around for the solder to flow through. So make sure you have always the right tools for these kind of jobs. So again, this is boring removing this, so once I am done, I'll show you the end result. There we go, success. So here's our little tiny module, which is our 12 volt standby DC-DC converter, and you can see it's a fully standalone converter, and it has only a couple of different pins. And during the removing of it, I can see some stuff came off the other board. So I'm gonna have to make sure that I solder this back very carefully and clean it really well. And most likely that was the problem from the interface. You can see there's some glue left over here. That was supposed to keep the board in place. I don't understand why they've done that, because this hole here was supposed to be some kind of a screw that would go through this plastic part. So I'm gonna I have some good Teflon screws that I can use, which can withstand high temperature, and I will screw it back in place using that. Hopefully it will come back to life. So I'm going to go ahead and clean that with some iso alcohol and so on, clean all the joints. And one of these pads came off on this side because it wasn't connected to anything. It's only connected on that side, which means soldering this is going to become a little bit more difficult, because I have to reach with the soldering iron and make sure that solder joint is really well done. So I'm going to go clean this up, and then I'll solder it back in, and I'll show you the final product, and we'll plug it back in. Hopefully it works, and then we can take a look at the rest of the unit. Alright, here's the finished product. So that I've just gone ahead and remove the solders, clean it up, and this one I cannot solder back again because of the fact that the solder is gone on, the pad is gone on this side. But that's okay, because on this side, of course, the trace is still there, and I've removed the plastic part of the connector, so I can really reach in and make sure that all the solder joints are nicely done. And I went ahead, and as I mentioned, I used a Teflon screw there to attach it, and it's glued nice in place with high temperature epoxy, and it looks good. Now it doesn't dangle around and move around anymore, which was I assume was the main cause of the failure, the fact that this was loose, and over various thermal cycles and so on, eventually maybe one of the connections broke. So let's go ahead and put it back inside the unit. And one other thing I wanted to show you just again, because this repair was, well, rather boring, I was hoping it would be something more interesting, but nonetheless we can still make something good come out of it. Let me talk about this IC, which I mentioned a little bit earlier. Let me show you what's inside this IC and how it's supposed to work, and it will serve to some extent some extra educational value of the repair, so that you can have an appreciation of how this main DC-DC converter works. And then I'll show you the motherboard and we'll see what happens. So here's the internal block diagram of the U3845, which is the main current mode controller for the DC-DC converter in this power supply. This is the first and most important component, which does the main conversion for all the other, and all the other voltages on that power supply are derived from this main power supply unit here. So what it does, it may seem a little bit overwhelming at the beginning, but really, if you think about it, what its job is to turn on this power MOSFET transistor on and off at a particular rate, when in combination with this inductor here, it's going to produce a desired output voltage. And this is typical buck converter type of DC-DC converter, which we've seen many times before. And internally it does that by sampling the voltage at the output, so it knows what the voltage it's happening, that is the voltage it is generating, and it feeds that back via a current sense input back onto the inside of the IC. And at the same time, this obviously has to have an internal oscillator, because it is doing PWM, so it has a certain operational frequency which you can adjust to achieve different kind of efficiency depending on the current and the type of inductors and the type of cores. There's a lot of different parameters that go into choosing the frequency of operation for a DC-DC converter. But here you can adjust that frequency of oscillation by choosing the value of R and C, and then you can change the type of waveform you're going to observe at these points by choosing those values. And then that is going to, in combination with the oscillator, is going to generate a square wave like so, is shown on the diagram here. And that square wave as applied to a logical OR with the signal that is the comparison of the desired feedback voltage to the current. So it takes all of that into account, and by doing an operation of OR with the oscillator, depending on whether this comparator is telling you high or low and so on, you're going to generate a PWM at the output. And these NPN transistors are nothing more than just the output driver to drive the power transistor. And you can see that there's no PNP because they can't really make PNP, so that's why they're using two NPN transistors. So that's it. It's very straightforward. You can see the voltage feedback at the input comes back here. It's compared to some internal 5-volt generator that's divided by 2 to get 2.5 volts, and that comparison is fed yet to another comparator which compares to the input current, and then ultimately at the end of the day you're going to get various waveforms as shown here. So this is the voltage that's going to appear on the RC transistor, and then the output is going to be a PWM. So if you like, this is an obsolete part because the power supply is rather old, but you can go ahead and take a look at this, and you can pick this IC up, and the DigiKey still carries this, and you can go ahead and make your own little DC-DC power supply. It's nice to play with these things, a lot of learning experience. Remember that the whole feedback path, there's a negative feedback in here, where if the PWM duty cycle is too high, then the voltage will go too high, and if the voltage is too high, then this voltage will go up too much, and then it will come back down and reduce the PWM cycle in order to achieve the desired voltage. So yeah, I just wanted to show you what's inside this IC. And there's some other protection circuitry in there. If the voltage reference is incorrect, and it disables it permanently, and you can add some additional circuitry to it in here to generate shutdown and all the other fancy things that's of course on that power supply. So you can disable, so when the power supply is not running, when it's only generating the standby, this is not on. As soon as you enable it, then this whole thing starts to run, and PWM starts to come out, and the voltage comes out of the transistor at the regulated value, and so on. So, just wanted to give you a quick look at this. So I'm going to go ahead and put the power supply back in the unit and turn it on, and maybe connect it to an oscilloscope and see what it looks like. And here's a quick look inside the unit itself. It's just flooded with a whole bunch of different ASICs. Most of them are digital. This is mostly a digital signal processing type of stuff happening in there with memory and so on. And then only at the very end there's a DAC and so on to put the signal to the output. Otherwise everything else is digital. You can see multiple Altera Flex FPGAs. You can see a TSP processor from Texas Instruments. You can use a Motorola, probably the main processor here, a whole bunch of different kinds of memory, a few different flash type memories here, and there's a firmware IC all the way back there. The fan is connected directly to the board. Here's the AC filtering coming from the outside. Some more memory in here. This is a controller, the ribbon that connects to the front. Everything is really restricted. Here's the other thing I wanted to show you. Here's the relay for the soft power on. If you remember when I showed this schematic, there was a relay. That's this relay that turns on and off, which enables and disables the power supply when you turn it on. You know, other than that, really straightforward. There's of course some PLL stuff happening in there too. Here's a oscillator here, which is the main oscillator they use, the main voltage control oscillator they use, and the crystal, 10 megahertz crystal, is all the way back there. So the PLL that's controlling this crystal is actually getting its reference from the 10 megahertz reference at the back, and you can see that it's in a big can. I believe that should be an oven controlled crystal oscillator, if not a temperature compensated oscillator. Other than that, you know, pretty nice and straightforward, nice neat layout, very flat. And there's the only DC-DC converter that I see is in here. A bunch of other different crystals around. This is some custom. This is either the DAC or the final amplifier. I haven't checked, but you can see that this is the main. This unit is custom, probably made by Agilent. You can see it's sitting on a custom ceramic substrate, and it's then attached to this. So if this goes, most likely replacement is not really possible. There's some other tuning inductors in here, some ferrite core used to perhaps flatten the frequency response for calibration and so on. I haven't looked at it. A whole bunch of other relays to switch to different modes of operation, and yeah, looks pretty nice. Now the only thing left to do is to close it up and connect it to the oscilloscope. Alright, here we go, all closed up, and voila, look at that. No problem at all. It seems to work without any issues. I haven't tested the output, we're going to test that next. But you know, it has a really rather simple interface. You can do, you know, sine, square, and ramp, and pulse, noise, and then under the ARB you can upload your own waveform, of course, or you can use some of the built-in waveforms like the exponential rise file, negative ramps, and sync and cardiac, and so on. So, you know, I think it should work. I don't think any other problems. It also accepts modulation, which you can have either internal or external. And we saw the modulation port at the back of the unit, and you can do AM and FM and all kind of different types of things. You can see, you know, I can choose AM, FM, or if escape, choose frequency shift keying, and so on. And yeah, you know, it seems pretty interesting. You can do sweep. You can start and stop at a particular frequency. You can do burst of number of cycles of a waveform that you're interested in having. And also, what you can also do that's you know, kind of nice is that if you press the graph button, it gives you a graphical representation of the waveform, so you can kind of have a visual feedback. This, at a time when this unit became available a long time ago, people weren't doing that yet. And you know, so when now that for example, the Regal DG4182 or the Agilent SDG5162, which are competing products, they do these now on a regular basis, of course, so it's not that novel. But you know, let's go ahead and try it out. Let's say I'm going to set this to, you know, we can go to 1 volt peak to peak, and we can set the frequency, let's say, to 1 where's megahertz, and that's it, no offset. And now, you know, you can enable or disable the output. So for that purpose, I'm going to connect the unit to, oh, here we go, to my Regal DS6104. That's going to allow us to make some measurements. So here we go, connect the output to the cable directly to channel 1, like so, pretty straightforward. And let me go ahead and focus on the, sorry, give me 1 second and get this camera right, there we go. There you go, now you can see it. I'm going to enable the output, and voila, not bad. Let me set this guy to 50 ohm, change the scale again, like that, and let's make some measurements. Let's say measure the frequency as well as the voltage peak to peak. There it is. Not too bad, look at that. There it is. You can see that it says exactly 1 megahertz, and voltage peak to peak is 1.02 volts. And it's not exactly 1 volt because there's some noise and other stuff that you know, is always on top of that. So the peak to peak from the scope is always going to be a little bit higher. So it looks fine. I can go ahead and increase the frequency. It's 2 megahertz, 3, 4, 5, 6, and so on. This thing is supposed to go all the way up to 80. So let's try 50 megahertz. And go ahead and do that again. There you go. 50 megahertz. The output amplitude has dropped a little bit. It's now 950 millivolt peak to peak. And I can go ahead, and now we're at 70. and 80. There it is, 80 megahertz, 950, pretty good. It still looks like a nice, reasonable sinusoid. So let me go back to 10 megahertz, and then I can try different kinds of waveforms. Here's a square wave, looks pretty good, nice. Just remember, this is in 50 ohms, of course. Here's the ramp. Oh, for the ramp, I guess you cannot go more than 1 megahertz. Okay, I don't know why. Oh, it's because of the sharp drop, I guess. Anyway, it's a little bit jittery at that point, but seems to be okay. Here's pulse with very, very narrow pulses. You can change the pulse width. Right now the pulse width is 992 nanoseconds and so on. You can change it, you know, you can make it bigger, you can make it smaller. So it looks nice. Here's some noise, 1 volt peak-to-peak noise, broadband noise, of course, and you can have arbitrary waveform. So this is the exponential rise, I believe. So let's go ahead to, let's say, cardiac. There you go. This is a cardiac waveform. You can put the trigger right here. There it is. You know, looks nice. It works really well, and I'm pretty happy with it. So there it is. I'm sorry that it wasn't as exciting of a repair as I initially hoped. I thought it would be maybe something more complicated. Didn't realize it was going to be something simple. But nonetheless, we went through the operation of it. Take a look at the power supply. It was still interesting to do, and now, you know, we've got another ARP here in the lab for future use. So as always, if you like the video, just spend 10-15 seconds, give it a thumbs up, leave me a comment. I always read them, and I appreciate all the nice things you guys say. And also, if you join the Twitter account, I have a Twitter account which I occasionally tweet, you know, some interesting trivia about electronics, and also post new websites on it, post new videos, links, and so on, so you can keep up to date with that. And you know, if you're ever interested in sending me something for repair, or sending me something to take apart or talk about in the video, let me know. You know, I can always try and do some of that as well. Take the load a little bit off of Dave, who's got so much stuff on his bench all the time. So if you're interested, let me know, and you know, I'll catch you up on the comment section. Take care.